So what if the biggest threat to your health was hiding in your next meal and it was completely invisible? We put a lot of trust in our food and water being safe, but the truth is, these microscopic dangers are a constant hidden challenge. And that really gets to a fundamental problem for safety all over the world. How do we actually detect these tiny bacteria that can make us seriously ill? How do you catch a culprit that's 1,000,000 times smaller than you are? And make no mistake, this isn't a small problem. Nasty bacteria like salmonella are one of the biggest causes of foodborne diseases on the planet. It's a huge risk to public health, and it's a constant battle to keep our supply chains safe from these invisible invaders.
All right, let's dive into our first section, an invisible danger. To really get a handle on the scale of this problem, you have to look at the numbers. This isn't just something that happens once in a while. It's a persistent, global threat. So get this. According to the World Health Organization, in 2021 alone, there were 58 separate food safety incidents caused just by salmonella, and that was across 86 member states. Every single one of those incidents could have become a massive outbreak, threatening people's health.
Okay, on to our next section, racing against the clock. Because when you even suspect a contamination, speed is absolutely everything. Finding the source as fast as possible is the only way to stop a small problem from blowing up into a huge public health crisis. It's a literal race against time.
And this is where we've always hit a major roadblock. You see, the current gold standard methods, the ones where you grow a culture in a lab, they work, but they are just so slow. We're talking 2 to 3 days to get a result. By then, the contaminated food could already be in stores or even in your fridge at home.
And this table just lays it out perfectly. Look at the incredible leap forward we're talking about here. The detection time plummets from days to under 45 minutes. The equipment goes from a whole laboratory to a small portable device. And the operation? It goes from needing a PhD to being easy enough for pretty much anyone to use. This is a total game changer for food safety. So our third section, building a nanotech detective. How on earth did researchers pull off this incredible boost in speed and portability? Well, they basically built a tiny detective on a nanoscale with one mission, to hunt down salmonella. So let's break down its 3 key parts.
First things first, every detective needs a body, a solid frame. The foundation of our little detective here is something called a covalent organic framework, or COF for short. Just think of it as a super strong, stable, and porous microscopic sphere. It's the perfect chassis to build on.
Okay, next up. Every detective needs a way to signal when they've found something, right? In this case, that's the job of these tiny gold nanoparticles, which act like a powerful engine. These little things are called nanozymes, and they have this really cool enzyme-like ability to kickstart a chemical reaction that we can actually see. And finally, we have the most critical part, the secret sauce, really. How does our detective know exactly what to look for? Well, it uses something called an aptamer. The best way to think about this is like a pair of custom-fit handcuffs that are designed to grab onto salmonella and absolutely nothing else. That incredible specificity is what makes this whole test so darn accurate.
So here's a look at how it all comes together. On the left, you see how chemicals are combined to form that base sphere, the COF. Then, that sphere gets decorated with those gold nanoparticles. That's our engine. And for the final step, the aptamer handcuffs are attached to the surface. And just like that, you have a single, powerful nanosensor ready to go on a mission.
All right, section 4, the color of contamination. So our little nanotech detective finds its target. How does it report back? There are no flashing lights or sirens. Instead, it uses a really simple, unmistakable color change.
So here's how the reaction works. If a sample is safe, no salmonella, the sensor's little engine just hums along freely, triggering a reaction that turns the solution a deep, dark blue. That's your all-clear signal. But if salmonella is present, those aptamer handcuffs snap right onto the bacteria. This gums up the works, basically jamming the engine and stopping that color change from happening. So a lighter color, or no color change at all, means danger.
And you can see the results right here in action. It's so clear. The vial on the far left, the one that's dark blue, that's the control. It's clean. But as you add more and more salmonella moving to the right, you can see the color gets lighter and lighter. This shows that you can tell not just if there's contamination, but how much contamination there is, just by looking at the color.
Okay, this brings us to our final section, safety in your pocket. Because look, all this clever science is fantastic, but what really matters is taking it out of the lab and making it practical for the real world.
Just think about the impact of that speed.
Less than 45 minutes to get a result. That's fast enough to do real-time checks at a food processing plant, a water facility, even a restaurant kitchen. You could stop an outbreak before it even has a chance to start.
And it's not just fast. It is unbelievably sensitive. This sensor can detect as few as 7 colony-forming units. That's basically 7 individual bacteria per milliliter. To put that in perspective, that's like finding a needle in a haystack, making sure even the tiniest trace of contamination gets caught.
And to make things even easier, the researchers developed a simple smartphone app. You just take a picture of the sample vial, and the app analyzes the color for you, giving you a crystal clear reading, safe, danger, or extreme danger. It completely removes the guesswork, putting the power of a laboratory into anyone's hands.
And this isn't just a theory either. This sensor has been successfully tested in really complex, real-world samples like milk and even lake water. That's the proof that it's robust enough to handle the messy challenges you find outside of a perfect lab environment. It's ready for prime time. So this all leaves us with a pretty fascinating question. This specific nanotech detective was built to hunt for salmonella, right? But its basic design, its framework, could be adapted to hunt for other things, different bacteria, viruses, maybe even toxins. So what happens to global health? What happens to our safety when a diagnostic laboratory can literally fit in the palm of your hand?